All right, let's have a little bit of a discussion. Let me see here. You can unmute yourself. Um, what are some nutritional roles of proteins? We'll talk about nutritional and physiological, and then we'll talk about physical. So what are some nutritional and physiological roles of protein that you remember from last time?
Maintaining and building muscle mass.
Right, that is physiological role. So yes, maintaining, preventing degradation of muscles in aging population, muscle growth in athletes, and muscle regeneration. Great. What else?
Bioactive, like antidepressant.
Yes, bioactive peptides, definitely. They have multiple physiological roles. Some are antidepressant, antihypertensive, anti-inflammatory. So peptides that originate from the hydrolysis or the digestion of proteins. Great. What else?
Essential amino acids.
Exactly. So the essential amino acid, so complete protein would have all of your 9 essential amino acids in amounts that are required by the body. So we call that complete protein. What other than essential amino acid is important about the nutritional quality of the protein?
Digestibility.
Yes, digestibility, perfect. So even if it's a complete protein, but if we have problems digesting it because of its structure or if it has been processed, so it's very polymerized and the enzymes can't reach it. So basically, even though it has all the essential amino acid, they might not be accessible if the digestibility is low. And hence that factor is taken into consideration in PDCAS. We talked about it briefly. We'll talk about it later in a different lecture, is the protein digestibility corrected amino acid score. So it takes into account the limiting amino acid and it also takes into account the digestibility of the protein. So very good. So we have the nutritional quality in terms of essential amino acid and digestibility and the amounts needed per day, which is on average 50 grams per day, is kind of the required amount for protein. And also the different physiological benefit, enhanced metabolism, satiety, other physiological benefits that you talked about. So great. So in terms of physical roles in foods, what can you list?
Color, like for browning?
Yes, color. Sometimes it's desirable, sometimes it's not desirable. And we have two types of color mechanism, either the Maillard reaction, which is non-enzymatic. It involves amine groups from proteins and reducing sugars. Sometimes it's desirable, like in bread. Sometimes it's not desirable, like in beverage, for example, browning over time during storage of a high protein beverage with a reducing sugar there. And then you have the enzymatic with the polyphenol oxidase, which is a protein because it's an enzyme. All right, so color, what else?
Taste.
Taste. I'm glad that you said taste, not flavor, because the protein itself doesn't really have a particular flavor. It may associate with flavor compounds that will be off flavors due to interactions with the protein, but can contribute to taste through bitterness, sourness based on the amino acid profile, um, and umami flavor, umami taste, I would say, sulfur note. So that is dependent on the composition of the protein, the amino acid composition, and if there has been a proteolysis, which will give you a distinct taste. Okay, good. What other than color and taste?
Emulsification and
Yes,
foaming.
now we're talking about functionality. So functional properties such as emulsification is one, gelation, solubility. We're going to talk about functionality quite a bit in this class and linking the structure of the protein to function with lots of examples and applications. Okay, great. So what are some intrinsic factors that impact protein structure? without looking at your notes, what do we mean when we say intrinsic factors?
Things like the actual structure of the protein.
Yeah, so the actual structure, well, the intrinsic factors dictate the structure or the configuration of the protein. So what dictates the protein structure is the amino acid composition and sequence. So that is an intrinsic factor. So it's not just composition, how they are in sequence in the peptide will impact how the structure is formed. And we'll talk about this today. It's part of today's lecture, is how sequence impact the structure, the secondary structure, and the tertiary structure, as well as quaternary structure. So intrinsic factors is amino acid composition and sequence. And this also impacts surface properties, a charge. So what would be the net charge of the protein at the neutral pH, for example? What would be the surface hydrophobicity of a native protein versus a denatured protein? So all of these are called intrinsic factors. Molecular interactions. The molecular interactions can be internal within the protein. We call them intramolecular interactions, or with another molecules would be intermolecular interactions. So you want to differentiate between intra and inter. It will come quite a bit as we talk about molecular interactions of the proteins. So these are all intrinsic factors that contribute to the native structure of the protein and the functionality of the native structure of the protein. But there are extrinsic factors that causes the protein structure to change, to go from native to denatured or modified. Can you name a few?
Temperature, pH.
Yes, temperature, pH. So let's say we are pasteurizing our protein before we dry it. So that's causing heat. Or when we dry it using spray drying, that we are incorporating heat. So heat thermal treatment. Also, when we formulate, we might be imparting thermal treatment. So that is going to cause protein to denature, potentially polymerize. pH is important. pH of the system, whether it is at the isoelectric point of the protein, it's acidic, too basic, is going to cause some interactions to be broken and some other interactions to form. Okay, what other than pH and temperature?
Salt be a factor?
Yes, salt, definitely. Sometimes a little bit of salt is needed to enhance solubility, for example. So in protein beverages, they add some phosphates to enhance the protein solubility. We call it salting in. Sometimes we use a little bit of salt to enhance protein extraction and isolation. So we solubilize the protein with a dilute salt. Sometimes we salt out the protein. A high concentration of a specific salt causes shielding of the protein, disrupting amino acid interactions with each other, so it can cause denaturation and limited interaction with water. So salt is very important. Sometimes a little bit of salt also enhances gelation, enhances emulsification. So we'll talk a lot about that later on. Okay, so salt, pH, temperature, what else?
Enzymes? Use
Enzymes.
of enzymes?
So yes, that will lead to modification of the protein. So basically breaking down of the peptide bonds and releasing peptides of small and large molecular weight that will impact surface properties and functionality. Great. So other modification techniques we're going to talk about later on in the semester. Okay, so extrinsic factor, basically whenever you formulate, there are different conditions that would put the protein under, including presence of reducing sugars, presence of fat, presence of solvents. So all of that will impact the structure and interactions. So great, we're going to spend a lot of time talking about extrinsic factors as well. Can you give an example or a couple of examples how change in protein structure may impact functionality? those of you that already work with relating structure to function might have an example to give to the others. We're going to spend, I don't think we talked a lot about linking structure to function last time, but after we cover all intrinsic factors and functionality and extrinsic factors, we're going to give you a lot of examples linking structure to function. But can anybody think of a change in protein structure and how it may impact functionality?
Water absorption.
Water absorption, yes, so it is a functionality. So water holding capacity and water binding capacity, it's a functionality. So definitely a change in structure like in denaturation, for example, that particular functionality will change. If you have a globular protein and it has really high surface hydrophilicity, such as whey protein, it's a very surface hydrophilic protein. So it has very low surface hydrophobicity. What do you think is needed for it to emulsify, to be a good emulsifier?
It needs to, the hydrophobic groups need to unfold. So maybe addition of some kind of a solvent or disruption that will help it to open up.
Exactly. So you need to do partial denaturation, either by heat or by any other method that might pH change. So you want, or work force, physical force, you just want to make sure that your protein opens up a little bit. So shear, temperature can lead to some partial unfolding that allow the protein to have a little bit better surface properties, balance between hydrophobic and hydrophilic residues. So depending on the final application, you want to see what do you need to do with this protein to make it function better. Sometimes it's change in environment, sometimes it's directed change to the protein structure itself. So what is the R group on an amino acid and how it may differ among different amino acids? So we're talking about the basic structure of an amino acid. You have an amine group, you have a carboxyl group, you have chiral carbon. Most of the amino acids have chiral carbon. Then you have an H, and then you have an R group. So what is that?
It can be anything. It can be another amino acid, which can lead to changes in the protein charge.
So it can't be another amino acid. So the R group is part of an amino acid, but it does impact charge. So you're correct. So the amino acid is, the R group is the chain, the side chain of the amino acid. And that side chain can be just a hydrocarbon chain, a long hydrocarbon chain that makes the amino acid not very reactive and potentially hydrophobic. Or it can carry an additional amine group or several amine groups, which makes it maybe positively charged as specific protein pH, or it might carry a sulfidyl group, or it might carry a carboxyl group. So the R group basically is the side chain that can have different functional groups or non-functional group that impact interactions either within the protein itself or with other molecules, water, other proteins, carbohydrates, fat, flavors, whatever it is. It's a very important component of the amino acid that dictates even the structure of the protein, which we will talk about. The secondary structure, the tertiary structure, steric hindrance. So it has a very important role in a lot of different things. We'll talk more about that. Okay, so this is kind of how we're going to start each lecture, is with recap questions. And also, if you have any questions from previous lecture. So it would be great to bring discussion points, examples from your research, anything that we've talked about and you want clarification. So this time, if you don't have questions, that's okay. But I'd like you to prepare something for next time we meet next Wednesday. Go through your notes and come with a discussion point, an observation, an example you want to talk about, a question for clarification on any topic. So since it's a Zoom class, I would like to make it a little bit more interactive by you coming in with some discussion points. We might not go through all the material, that's okay. I can record lectures if we run out of time, but I want to encourage more discussion amongst us at the graduate level class. That's the most, you know, that's how we learn. We learn from each other. I learn from you, you learn from each other. So please keep that in mind for next time. Okay. Here are a couple of questions before I dive into the material today. So a soft drink manufacturer wishes to fortify their beverage with protein. So they basically want to produce a protein beverage, and they want that protein beverage to be acidic. What dairy protein you think would work best, and why do you think? What's the golden standards of protein beverage? Which protein is the golden standard?
Whey protein.
Yes, absolutely. Whey protein is the golden standard, and you can't imagine how many requests I get to make plant proteins act as whey protein. So far, they can't. But we're working on modification techniques to make them not necessarily act as whey, but be able to be soluble at acidic pH. So whey protein is your golden standard. Now, why? We'll learn about that when we cover whey protein and when we relate structure to function. I already said earlier, whey protein is very hydrophilic on the surface. It's a small globular protein. So its molecular weight, well, you have beta-lactoglobulin is the main protein in whey protein ingredient. You have alpha-lactalbumin, you have other minor proteins, but mainly the beta-lactoglobulin and alpha-lactalbumin, they are really small globular proteins, molecular weight 14 kilodalton to 16 to 18 kilodalton. So these are considered low, and they are present either as monomers or dimers, depending on the pH. They can be octamers. Beta-lactoglobulin can be present as octamer, but that's when you have a pH close to the isoelectric point. So because of the high surface hydrophobicity, the globular structure, the small molecular weight, it remains soluble and clear. So the solution is clear. So the acidic pH, which is pH 2.5 to 3, sometimes 3.2, 3.4, depending on the formulation. So that pH allows the whey protein to be soluble, and not only soluble, but clear. So you have this nice clear beverage that you can put in a plastic or glass container that is visible, see-through, so the consumer can see the beverage, no sedimentation, really nice clear beverage, and high in protein, where you can claim an excellent source of protein. Okay. So you have a muffin ingredient declaration. So basically the list of ingredients listing sodium caseinate. Why do you think sodium caseinate was added to a muffin? Usually you have a little bit of flour, eggs. I don't know what are the ingredients of muffin, but why do you add sodium caseinate?
Maybe for water capacity.
Say that again, what?
Maybe for water capacity.
You're very close here. Viscosity, I want to say. So interactions with water and give the batter a viscous, increase the viscosity of the batter. And also we will learn about casein. It's a natural emulsifier. So when you have the muffin, you have fat, you have aqueous, you have different components, but you have a lot of fat in there. So caseinates in their structure, they have a really nice open structure with a very nice balance of hydrophobic to hydrophilic residues on the surface. So that makes them very good emulsifiers. So they're added to enhance the viscosity of the muffin and also to enhance emulsification. All right. So these are just introductory kind of examples, but like I said, we'll have plenty of examples throughout the semester as we talk about structure, then function, and then the different proteins. So it will be rich with examples. Okay, so again, this is the kind of the diagram that talks about the entire class, entire course. And you'll see it a lot. And I showed it to you last time. Linking structure to function and looking at the factors that impact the structure and understanding the functionality and how the structure impacts functionality. So by the end of the semester, you'll be experts in linking structure to function and understanding different proteins and how they impact functionality. So we will start with intrinsic factors. Okay, so today we'll cover as much as we can with intrinsic factors. I'll keep an eye on the watch here so that I can give you a break midpoint, and I'll try not to forget like last time. I can get carried away. Okay, so with intrinsic factors, we talked at the beginning of class, it has to do with composition of amino acids, but most importantly, the sequence and the size, like how many amino acids you have, how big is the protein, how many ionizable and reactive groups do we have available for interactions. So ionizable groups, meaning groups that can carry charge either by giving up a proton, like the carboxyl groups, and become negatively charged, or picking up a proton and becoming a net positive charge, like the amine groups can pick up protons. And at low pH, the carboxyl groups will pick up proton, and you have a positively charged amine groups, then you get a net negative, a net positive charge. So it's very dependent on the pH as well. But you might have extra additional ionizable group based on the different amino acids you have in the sequence. And what other reactives group you have? Do you have hydroxyl groups? Do you have sulfhydryl groups? So this is important, and we'll talk about that. Hydrophobicity. So there's a total hydrophobicity and there is a surface hydrophobicity. When we say total hydrophobicity, we mean how many amino acid, percentage of amino acid that are hydrophobic in your sequence or in your protein. If let's say you have higher than 30% hydrophobic residues, that means this is a protein that have high tendency to polymerize via hydrophobic interactions and potentially form irreversible polymers. So hydrophobicity, surface hydrophobicity is what's on the surface of the protein. The native protein, do you have, how many residues do you have that are hydrophobic that wind up on the surface of the protein? That can dictate surface activity. Conformation, what do you have? Do you have a globular shaped protein? Do you have an open structure? Do you have a quaternary structure where multiple proteins associate to form a quaternary structure like a casein micelle, for example? What type of molecular interactions do you have within the protein itself and potential to interact with other components? So we're going to talk about all of these intrinsic factors and how they impact the protein structure. Okay, so intrinsic factors, the proteins differ. There are a lot of different proteins. So how do they differ? They differ in amino acid composition. But not only that, they differ in sequence of amino acid, okay? And this means they differ in configuration and they differ in chemical biochemical properties. So in chemical biochemical properties, or basically you might hear me say physical chemical properties. That's common to say, a physical chemical property. That means the hydrophobicity, whether it is on the surface or total, the net charge of the protein and the surface charge of the protein. So you hear me sometimes saying surface charge. which can dictate how the protein interacts, or the net charge, which is just dependent on the amino acid composition and also dependent on the pH of the system. So all proteins differ in these characteristics. And then when they differ in these characteristics, they're definitely going to differ in structure, and therefore they're going to differ in functional contribution. That's why it's very hard to make pea protein act like whey protein. They're physiologically different. They are physicochemically different. So we cannot have one protein act like another exactly, but we can change conditions to make them function better. All right, so we're going to start from the very beginning. And I know this could be a review for many of you, and some of you have forgotten all about it. So it will be a good reminder of the amino acid basic structure. Here's the thing that you might not like, but it is important for this class, is to learn the amino acid structures. So there could be a question on the exam that I ask you to draw a sequence of a peptide. I want you to know the amino acid and become really knowledgeable in them because they are important in the structure and interactions. So you want to know what a lysine look like and why a lysine is more reactive in a maillard reaction, for example. So you want to know the structure of a lysine. You want to know the structure of a cysteine, which is very important in protein stabilization of the structure and molecular interactions. So that's why I want you to learn. It's not hard. Once you know the functional groups, you will remember them. Okay, so going just a refresher of amino acid structure, we have an amine group, we have a carboxyl group. So, and then we have something we call chiral carbon. So the chiral carbon is called chiral because every bond, so carbon has 4 bonds, every bond has a different group. So amine, carboxyl, hydrogen, and your side chain. The only amino acid that doesn't have a chiral group, who can tell me which amino acid does not have a chiral group? From anything that you remember in your food chemistry or biochemistry or any
Glycine.
Glycine, thank you. So glycine doesn't have a chiral. It's the smallest amino acid, and the R group is basically H. So glycine has the smallest molecular weight of 75 Dalton. So it is the only amino acid that doesn't have a chiral carbon. Okay, and this is usually in nature, your amino acid has an L configuration. That means you have your amine group to the left and the carboxyl group to the right. At neutral pH, what you have generally, you have your carboxyl group is deprotonated. That means it gave up its proton, so it is COO minus. And the amine group hold on to the proton, and it is positive. So the R group determines whether the net charge is going to be 0 at neutral pH or whether it's going to be positive at neutral pH or negative at neutral pH, depending on the functional group of the R, depending on the functional group in the R group. Okay, so this is a basic because it kind of takes up protons. And this is acidic. This gives up proton. So having a basic and an acidic group makes the amino acid a buffer. And that's why this is when you hear that proteins are good buffers. That's why, because of the carboxyl groups and amine groups. So they resist change of pH. So have a protein solution and try to titrate with an acid, for example. When you titrate with an acid, your amine groups are already protonated. Your carboxyl group will start picking up the hydrogen, then there is no change in pH. If you're titrating with a base with NOH, so the OH minuses in there are going to try to pull protons from the amine groups, and the amine groups give up their protons, and then you are then again not changing the pH very much unless you protonated all of your carboxyl groups. Then you keep adding acid, then the pH becomes acidic. And so, and you pulled all of the hydrogen. If you're titrating with an NaOH, then you adding more NaOH will make the pH basic. But because of the presence of these two, this becomes a very good buffer. R group. So again, we talked about the importance of R group. So it determines polarity. So is it a large, long chain hydrocarbon? That's going to be hydrophobic. Does it have a charged groups? This is going to be polar with charge. So, and it's going to determine reaction. Does it have a sulfhydryl group? Does it have an OH group? So that will determine interactions. So R group is a very important component in terms of forming the structure of the protein, as well as interactions within the protein and external to the protein. Okay, you guys can ask me if you have any questions. I can slow down, I can repeat the concept. Please do, if you have any questions, do let me know. Okay, so let's categorize our amino acid by hydrophobic, non-hydrophobic. But with hydrophobic, there's also a class of aromatic and then a class of aliphatic. So the aromatic are components that have an aromatic group, obviously, and they absorb light at 280. So if you have a protein solution and you want to get an estimate of a concentration and you know that your protein solution is pure, you can do absorbance at 280 and get a concentration if you have a standard protein. So it is a common method of analysis for proteins is measuring absorbance at 280. And this is because these specific amino acid absorb light, and mostly all proteins contain some amount of these amino acid. So all proteins absorb UV light, except if you have peptides. If you've broken your proteins into peptides and you fractionated the peptides, not all peptides may contain these aromatic amino acids, so you might not see absorption at 280. At that case, you can measure absorption at 220, which is specific for peptide bonds. Okay, so tryptophan has the highest molar extinction. So tryptophan is the one that absorbs the most UV light, then followed by tyrosine. Phenylalanine has lower molar extinction. Tyrosine is very important in terms of reactivity because of its hydroxyl group. It can be ionized at alkaline pH. Later on, when I show you solubility curve, for example, for soy, you'll see that at alkaline pH, soy protein is more soluble than at acidic pH. Why? Because at alkaline pH, your OH becomes O-, and that causes more interactions with water. These are the other hydrophobic amino acid, but these are aliphatic because you do not have a ring structure. Now, proline is not a ring structure, but it is a cyclic structure. So the uniqueness of proline here, okay, so here I'm just showing you have a sulfur group in methionine. It'll come back later. And in isoleucine, you have 2 chiral carbons. And then proline. Here's where I want to spend a little bit explaining proline. So if you see here, you can see my mouse. Every amino acid has a primary amine. Okay, so a primary amine is defined. This is missing its plus here. There should be a plus. A primary amine meaning its nitrogen is having one bond with carbon. The rest of its bonds are with hydrogen. And primary amine is more reactive than secondary amine. This is a secondary amine where its nitrogen has two bonds with carbon. So one here and one here. And then you have, I'll show you later, a tertiary amine where the amine group is bonded to 3 carbons. Okay, so proline, you can see it does not have a primary amine. Its amine group is linked to the R group. So the R group formed a cyclic form with the amine group. This is important, and we call it a secondary amine here, and we call it a unique structure because it is a very, it gives a very rigid structure of a protein. So if you have a proline in the amino acid sequence, it kind of have less flexibility in rotation. And because you have less flexibility in rotation, it impacts the secondary structure. So we often call proline, you hear me say, secondary structure breaker. So when you have a lot of proline in the structure of the amino acid, you don't form alpha helix or beta sheet. You form mostly random coil. And remember that when we talk about caseins later with an open structure, it has a 17% proline in it. And that is why it doesn't have a lot of alpha helix and beta sheets. It's mostly random coil and open structure because of the rigidity that that proline brings. Another thing here I want to point out is this hydroxyproline. Some proteins have post-translational modifications, such as in collagen, for example. You have hydroxyproline in there. Okay. Let's talk a little bit about the hydrophilic amino acids. So we have the charged polar and we have the non-charged. So these are the charged and they're very important for different reactions, and I'll give you examples here. So we have the positively charged, the histidine, the lysine, the arginine. If you look at lysine in particular, it has 2 primary amines. This amine right here might be involved in a peptide linkage, which is very common. And it could be like in the middle of the sequence of the protein, but it still has a primary amine. Why is this important? It's important in reactions like this, the Maillard reaction. You must have heard that lysine is the most reactive amino acid in Maillard reaction because in a sequence, this primary amine is taken up in a peptide bond. You still have this primary amine, which is very reactive. It will be readily reacting with reducing sugar, causing the browning and nutritional loss of the lysine. So excessive processing and a blockage of the lysine via Maillard reaction cause nutritional loss of the protein. But there's something unique about this lysine, and I'll mention later. Look at this hydrocarbon chain. It's really long, which you might think, oh, that might cause it to be hydrophobic. Yes, this long chain of hydrocarbon tends to associate via hydrophobic interactions. So in a protein sequence, you see that this side of the lysine might be protruding to the outside. This positively charged amine group might protrude to the outside of the protein, while this large hydrocarbon or long hydrocarbon might be in the interior of the protein.
I have a question.
Yeah.
Back on the other slide, so in the Maillard reaction, when you have the nutritional loss of lysine, like what happens to what's left over? Like what was lysine?
So the lysine basically reacts with reducing sugar and you form a Schiff base. And with that, then that would be the initial state, and the Amadori compound is formed. And that compound is no longer just free amino acid. It is reacting with the sugar. You get a different compound. So it won't be nutritionally available as this lysine amino acid. And if you have advanced stages of the Maillard reaction, then you get different sets of polymerization and formation of intermediate products that's no longer lysine anymore.
Okay, thanks.
Yeah. Okay, so I want to go back here a little bit. So you also have the basic and you have the acidic. So the basic amino acid basically have additional amines in their R chain, and the acidic amino acid has additional carboxyl groups in their R chain. Okay, so that makes them acidic at neutral pH. That means they carry a net negative charge at neutral pH, and the basic amino acids carry a net positive charge at neutral pH. And here also there is hydroxylysine. That's another derivative of lysine that can form during post-translational modification, also found in proteins such as collagen in meat. So other polar amino acids that don't have a charge, but polar because they have a short chain, R chain, and they have a group that can potentially be ionized. So this one is a hydroxyl group here. Glycine, for example, is small. That's what makes it polar. You don't have really a side chain that is hydrophobic. And this is a small side chain and also have a hydroxyl groups. And here you have the glutamine and asparagine, which if you have acid or alkaline hydrolysis occurring, if you put them in a concentrated acid or concentrated base, they give up an amine group. They get deamidated here, and let me see. I have and then here. So you lose the amine group, and then they become glutamic acid and aspartic acid. So the serine and threonine are important because of their hydroxyl group, especially in post-translation modification. So when we talk about casein later on, we're going to learn about alpha caseins and beta casein, and alpha and beta are phosphorylated. So the serine and threonine amino acid in beta and alpha casein has a phosphate group. So the OH group, the H is replaced by a phosphate, and then you get a phosphorylated alpha casein or kappa casein. Why is that important? It's important in the formation of the micelle because you form the calcium phosphate bridges that stabilizes the internal moiety of the casein micelle. And then also serine and threonine can have post-translation modification to be glycosylated. So they will be glycosylated. Protein is an example is kappa casein is glycosylated. We also have beta-conglycinin, let's say in soy, that is glycosylated as well. So this glycosylation gives stability to the casein micelle because now the kappa casein has a higher net charge due to the presence of this glycosylated fraction of kappa casein, and it is on the surface of the micelle. So that stabilizes the casein on the surface, making sure that you have a colloidal system in milk and the casein micelles don't aggregate. So it's very important a contribution of serine and threonine, for example, in this particular system, which is the casein micelle. Cysteine. So cysteine has a sulfidyl group. So we call this sulfidyl group, SH group. It means the same thing. Thiol group. Thiol is another name for a sulfidyl group. It's very important in stabilizing the tertiary structure of a protein. So if you have cysteines, then you have internal, so intra disulfide linkages that increases the energy needed to denature the protein. So it causes stabilization of the tertiary structure. On the other hand, the presence of free thiol is important during processing. Sometimes you want to induce oxidation to form cysteine, or some people pronounce it differently. Some people say cysteine, press, press the ine, and sometimes they call this cysteine, and this is cysteine, or you can call this cysteine. I don't know. But anyway, the one without an E is a 2-cysteine amino acid that are linked via disulfide linkages. And you can reduce that by a reducing agent. So you can add beta-mercaptoethanol, DTT, sulfide group, so you can break it down back to the original cysteines. So this is relevant when we talk about cereal proteins and formation of gluten, for example. When we mix the flour and water and apply physical force, we're denaturing the gliadins and glutenins. So they come together once they're denatured by hydrogen bonding, and when they are in close proximity, the free sulfide groups oxidize with each other and form disulfide linkages, and then you get that nice matrix, the gluten matrix. But sometimes it's not desirable. So when you denature whey protein, for example, it opens up, and inside of that moiety you have a free thiol group, free sulfide group. So when you heat and for a long time and you have high protein concentration, over time or during even heating, you get polymer formation. This is not desirable for a beverage, for example. So polymerization is not desirable in certain applications, but they are desirable in others. So they are desirable sometimes in forming a strong gel for gel application, and they are obviously desirable in gluten formation.
I had a question.
Yeah.
If a flour like intermediate wheatgrass has high free thiols, can we say for sure that all the thiols participate in gluten network development?
That's a good question. So if you have high free thiol, there is a potential of polymerization, but what plays an important role in the gluten formation as well is the molecular weight. So from studying intermediate wheatgrass, there is different profile of the gliadins and glutenins in terms of molecular weight. So in intermediate wheatgrass, there are lower molecular weight glutenins. So while they can form disulfide linkages, they are not large enough to form that stable matrix. And there is also a difference in concentration of glutenin to gliadins. So glutenins usually are the ones that are needed to form highly disulfide linkages with high molecular weight. If you have high level of gliadins to glutenins, although you can form disulfide linkages, but you don't form a really nice matrix because of the lower molecular weight. Does that answer your question?
Yes.
Okay. All right. So, example of an application where the glutamine and lysine interaction is important. For example, try to make rice bread. It doesn't have the gluten forming proteins, so you don't have a really nice volume form because you don't have those large molecular weight proteins that can associate in a way to give you this viscoelastic property. You can add something to it to help it. So transglutaminase is an enzyme that promotes interaction between the amine group of a lysine. Here's your lysine in one polymer or one protein molecule, and another protein molecule that has glutamine. And the glutamine has a carboxyamide group. So this is a carboxyamide because you have an amide group here, amine group. So that's glutamine. So this group reacts with this amine. You give off ammonia and you form a covalent bond. So you form a covalent bond because between this carboxyl group here and this amine group there, and you release ammonia. So this transglutaminase is an enzyme that enhances this reaction, and you enhance polymerization that way. Then you can form a rice bread that has some volume, basically. Acid-base properties, I'll give you a break in a minute here. I'll finish the acid-base properties. So if we look at the amino acids, so here in this case, serine, when you have, let's say, neutral pH, you have, this is positively charged, this is negatively charged. You don't have any charges in the side chain. So you have a net charge of 0. Okay, so close to neutral, but you have 2 pKa's, all right, so which is a pH at which you have 50% dissociated and 50% non-dissociated. So remember what a pKa is. It is the negative log of the dissociation factor. Okay, so the carboxyl group has obviously an acidic pKa. That means then when you have a pH lower than 2.21, most of your carboxyl groups are going to be protonated, okay? Then you end up with a positively charged amino acid below the pKa of 2.2, okay? Above the pKa of the basic group, which is the amine group, so the dissociation here of the proton from the amine group. So this is basic, so you have high pKa. A pH above that, then your amine group is going to give up its proton. And already this one gave up its proton because it's acidic, so it gave it up sooner. Then you end up with a negative charge. Now, if we want to figure out the isoelectric point of serine, so this is how you would do it. So it is the pKa of the acidic group plus the pKa of the basic group divided by 2, you get the pi. So you have this table here that shows you the pKa of the carboxyl groups and amine group of all amino acid. Obviously, the acidic group are all in the acidic pH range, and the pKa2 for the amine groups are all in the alkaline range. Now you have a side chain pKa. So the basic amino acid, arginine, histidine, and lysine, and the acidic amino acid, aspartic acid, and glutamic acid have a third functional group that can be ionizable. So you get the third pKa. So the arginine, lysine, and histidine have a basic one. So this one here, and the histidine here is, it's not so basic, it's close to neutral, but the lysine is basic as well. The tyrosine has pKa. Why? Because of the OH group. So the OH can get ionized at alkaline pH. Okay, so the glutamic acid and the aspartic acid have acidic pKa because of the additional carboxyl groups. So this becomes important because when you want to determine the pi of an amino acid that is acidic, then you take the pKa of the carboxyls groups, the regular carboxyl group and the carboxyl group in the R chain, you divide it by 2, you get the pi. And then for the basic amino acid, you take the pKa of the amine group and the pKa of the amine group in the R chain, and you divide it by 2. So going back here, for example, 2.77 is the pi of aspartic acid, because if you take 1.88 plus 3.65 divided by 2, you get 2.77. Now, you might wonder, well, in a protein, it's much more complicated, and we're going to not go into there because you have so many amino acids in the sequence, and you have to take into account all the pKa's and the net charge, obviously, of that protein. So it gets really complicated. One last thing before we break here is the nomenclature of an anion, Zwitter ion, and a cation. So this is unique for every amino acid. The isoelectric point doesn't have to be 7. Every amino acid has different isoelectric point. But just here to show you that when you have one positive and one negative charge, then you have a Zwitter ion and a net charge of 0. And that is the isoelectric point. But then when you titrate here with NOH and you exceed the pKa2, then you start having, this one's, the amine group will lose its proton. Carboxyl group already lost its proton, so you get a net negative charge. And here, if you titrate with an acid, then you go over or under the pKa of an acid, then you get mostly a positively charged or a cation. So you just want to remember the nomenclature and at what pH you might have a net negative charge and what pH you might have net positive charge. You always have to remember above the isoelectric point, it's mostly net negative charge. Below the isoelectric point, it's mostly positive charge. And with pKa, also above the pKa, you're going to get mostly negatively charged. And below the pKa, it will be positively charged. So you want to remember those differences, take note of that. And I'm just going to give you now a 5 minutes break, stretch, do whatever you want, and come back, let's say at 4. So 6 minutes break. Okay, so we have everybody back. Brigitte, are we missing someone today?
Ellie, are we missing someone today?
No, everyone's here.
Okay.
Karthik isn't, but I don't know if that counts.
So we have 13 students in the class and two audits. And Ben, we should have 13, we should have 17 people on the participant list.
The 3 audits includes Karthik.
No,
Who's not?
two audit and Ben is sitting in. So we have Prince and Sonali audit and Ben sitting in, and we have 13 students in the class. That should be 16 and me 17. Who are we missing? I just want to figure this out out of curiosity. We have Holly, Devin, Brigida, Radhika, Grace and Nigel, Chrissy and Leslie, and Laura and Paul.
I think we have 17 now. I think Maud was missing.
Ah, I see. Okay, good. Thank you for figuring this out.
Sorry for that.
It was gonna bug me. Okay. All right. Okay, let's go back. I'll share my screen again. All right. So we're going to move on and talk a little bit about hydrophobic properties. So let's see, so hydrophobic properties of amino acids affect structure of the protein, fat binding properties of proteins and peptides, and solubility. What do you think? All right, we got some responses by text. G, okay, good. Yes, it's all of the above. We're going to talk about why it's impacting structure. It's actually a main driving force for the structure of the protein. And we'll talk about that later. Okay. So hydrophobic interactions, which ones are true? Hydrophobic interactions are the main forces driving the formation of the protein secondary structure. Disulfide linkage stabilizes the protein's secondary structure. Hydrogen bonds are the main interactions in alpha helix and beta sheet, which are secondary structures. What do you know? I don't expect you to know or to remember, but what do you know? Let's see. We're having people responding. A lot of C's, well, at least 2 C's. 3. I'm still waiting for the correct answer. I'm not seeing a correct answer so far. Okay, which is fine. That's why we're here. Let's see if we got yes. It is F, Kenzie. Okay, so we'll see why hydrophobic interactions are the main forces driving the formation. So the stabilization of the secondary structure is by hydrogen bonding mostly. Stabilization of tertiary structure is by disulfide linkage. But I'll show you a diagram to explain how the hydrophobic interactions are actually behind the formation of secondary structure. Okay, we'll talk more about that. So the correct answer is A and C. All right, so in general, hydrophobic residues do not want to associate with water. So you form hydrophobic interactions, and most, I'm not going to say all, because you do have proteins with surface hydrophobic residues, but most of the hydrophobic amino acid are going to interact with each other and hide from water. So a lot of the hydrophobic amino acids are going to reside within an interior moiety of the protein. Okay, and then hydrophilic residues will reside, again, I'm going to say mostly on the surface, okay? That doesn't mean that you don't have hydrophilic amino acid inside of the protein moiety, but this is kind of a general scheme where you have protein-protein interaction via hydrophobic interaction hiding away as much as possible from aqueous, from the aqueous environment.
What if they're not in an aqueous environment?
If they're not in an aqueous environment, good question. If they are in an organic solvent, the protein denatures and the hydrophobic groups are going to expose themselves to the solvent because now they want to interact with the solvent. So that's why organic solvent is actually a denaturant of the protein. But when the protein is formed in a cell, it's formed in an aqueous environment where you have water. So that's why it tends to form this kind of structure.
Thank you.
Yes, good question. Which brings us to this. Everybody loves delta G, huh? I really don't like delta G. It's just kind of confusing sometimes. So I don't want you to pay too much attention to it. There's delta G of hydrophobicity, and there's delta G of denaturation, and there are so many different delta Gs. So anyway, in here, what I want you to remember is what is the hydrophobicity? Is really the chemical potential of interaction of amino acid with organic solvent minus its chemical potential of interaction with water, basically. So if you have a positive delta G, then it's hydrophobic. If you have a negative delta G of hydrophobicity, that is, it would be hydrophilic, okay? Because then you would have more interaction with the solvent and less interactions with the water. Then you get a positive, with an exception of lysine. We talked a little bit about lysine earlier. It does have a positive delta G, although it's a polar amino acid, but it's an exception because of its long chain of hydrocarbon, which tends to like the hydrophobic or like a solvent. And then the amine group will be protruding to the outside. So this tends to form hydrophobic interaction, this long chain of hydrocarbons. That's why it's an exception, basically. Here, which I don't want you to pay too much attention to it, but it shows you something really interesting here. Why you say that the delta G of valine, for example, this is a valine, is equal to the delta G of glycine, because this part of it is glycine and the side chain, this part of it is the side chain. Okay, so basically this is showing you that the delta G of the chemical potential of interaction of valine is glycine plus the side chain. There's not much to it. It's just take it as FYI. I don't feel like it's very relevant to stuff we're going to talk about. Okay, so here are few reactive groups that are going to be very relevant to us when we talk about formation of secondary structure, tertiary structure, interaction, intramolecular, intermolecular, or interaction with other chemicals or in the environment. So, of course, the reactive groups, amine groups and carboxyl groups, are reactive functional groups in every amino acid. So they carry charge, they form a peptide bond, they form electrostatic interactions if they were terminal amine or terminal carboxyl. So these are important. Now, another one is very important. We talked about sulfidyl groups. So keep it in mind, it stabilizes tertiary structure. It forms molecular interactions, sometimes desirable, sometimes not desirable. Phenolic. So this is phenolic group, and phenolic groups causes hydrophobic interactions, absorptivity at UV light, and then you have the hydroxyl groups that are important they can be ionizable at high pH, and those specifically of serine and threonine can be part of post-translational modification. There's the thioester, which is in methionine. It has to do with, it takes part in chemical modification, same as with histidine and arginine. Histidine is the imidazole group, and guanyl is the group in arginine, this group. So, but most importantly, that you'll see come up a lot in anything we talk about later is amine group is the most reactive group, carboxyl, sulfhydryl, phenolic, and hydroxyl. So these top 5 are the most important for future discussions and reactions. So these functional groups impact hydrophilicity, hydrophobicity properties, function interactions, and thus functional properties of the protein. So keep that in mind here, this note. This is a table that shows reactions of these functional groups and their chemical reactivity and how they impact some functionality. So acetylation, succinylation, thiolation, these are chemical modifications of the protein. We'll talk about a modification at the end of the semester. It's the last topic. And chemical modification is a very old form of modification of the protein. It is no longer here approved in the US or North America to be used for modifying protein. It can be applied still in certain area of the world, like in China, for example. They can still modify proteins by chemical modification. So here's just I'm showing you a couple of examples just to see what reactive group take part in this particular chemical reaction. So acetylation, which is a reaction between an acetic anhydride and amine group. So again, here it emphasizes the amine group importance, where you can eliminate a positive charge, because the amine group at certain pH will have a +1. So with reacting with acetic anhydride, you end up with a product with +1 positive charge. So in this case, you are indirectly increasing the net negative charge of the protein, or reducing the total charge on the protein that might enhance hydrophobic to hydrophilic. For example, balance that might enhance emulsification, for example. Succinylation is you add succinic anhydride. Again, it reacts with the amine group here. And in this case, it adds a negative charge because succinic anhydride carries a charge. So then we are introducing a net negative charge. So we're increasing directly the net negative charge, therefore may enhance solubility, for example, because now you have a more charge on your protein. Thiolation, for example, is a reaction with a particular compound that adds a thiol group to your amino acid. Okay, so here you're adding a thiol group and it's reacting with the R chain in this case. Okay, so here's the reaction is with R chain. You're adding a thiol group and it eliminates a positive charge. Actually, yes, it eliminates a positive charge and it initiates thiol group at a lysyl residue. So basically, you have a thiol group, so you enhance chances of polymerization. Another example is blocking thiol groups. If you want to eliminate or reduce chances of polymerization for certain application, you can add a blocker. So a reagent that will react with thiol group and oxidizes the thiol group Therefore, it won't be available for interactions. Okay. Other reactions that involve amine group, again, that's why I say amine group is one of the most important reactive groups, is used in quantification or determining amino acid composition, for example. So you want to react the amino acid after you hydrolyze the protein. You want to determine amino acid composition. So the amino acids are reacted with anhydride, and anhydride is a compound that reacts with the amine group. And then you end up breaking compounds and forming a new compound that would absorb at 570. For proline and hydroxyproline, the absorption is measured at 440. So it's basically anhydride is used as a detection methodology to quantitate amino acids. This one is a common reaction we use for multiple purposes, which is reaction with ophthaldialdehyde or OPA. So again, it's a reaction with the amine group. So your OPA reagent reacts with the amine group and gives you a compound that absorbs light or fluoresces. So it absorbs at 380 and fluoresces at 450. So we use that for different purposes. One purpose is to determine degree of hydrolysis. If you have a protein and you want to determine how much of the peptides have been broken, you can determine that the more you have reaction, that means you have more free amines. That's an indication of peptide bonds being broken. So this OPA is used to determine degree of hydrolysis. You can also use OPA to determine if you have blocked amine groups in your protein. So if there's been a process, let's say you had transglutaminase reaction where lysine is reacted with the carboxyamide of glutamine, and you want to determine how much reaction happened, how much polymerization happened, you can determine that using OPA. It determines how much amine got blocked by this covalent linkages. Or if you're processing and you want to determine how much Maillard reaction occurred, because again, amines are blocked by reacting with reducing sugar. So yes, so it's very common methods we use when we want to react to determine either blockage of amine groups or determining if we have hydrolyzed the protein and how much hydrolysis happened. So very common reaction. Another reaction is with fluorasamide or fluorasamine. Again, it is a detection of free amine. Like OPA, it's a different reagent. And again, you form a fluorescence and then you measure fluorescence. Again, the reaction is with amine group. Okay, so we're going to move on to talk about building the protein structure. So we talked about amino acids. Now we're going to build the structure from primary to secondary to tertiary to quaternary. So we start with the primary structure. Again, this is review for many of you and not much new information, but it's good to remember them for the next chapters of this class. Okay, so the primary structure is basically the chain of amino acids. So the chain, the sequence of the amino acid, the linear form of the polypeptide. So basically we're forming peptides and it is a condensation reaction. So when it happens, you have amino acid plus amino acid, you get a peptide, you get one molecule of water. So this reaction has a high equilibrium constant, meaning it's not really reversible unless you apply energy. So when you form a covalent bond, it is not really a reversible reaction unless you have some sort of high energy to reverse it back to the amino acids. So you want to remember that covalent bonds contain a lot of energy and not easily broken. So you have high reaction constant, basically. Equilibrium constant, I want to say. Okay, so the peptide bond is basically the covalent interaction between a carboxyl group and amine group. So here's your first amino acid. So you have your chiral carbon here, you have your amine group, and that chiral carbon is also linked to the carboxyl groups. So, and then that's where the bond happened with the amine group of the second amino acid. And again, this is your third amino acid. At every bond formed, you have H2O lost, okay, for every peptide bond formed. So that is the definition of a primary structure, is basically your linear sequence of amino acid, and the peptide is basically a reaction, a covalent reaction between your carboxyl group and amine group. And often it is an L configuration on conformation where your amine group is the left and the carboxyl group of the peptide is at the right. So what you want to remember is the average molecular weight of an amino acid. Like we said, glycine is about 75, for example. So it's very small, but you do have larger amino acids. But then the average is around 135 kilodalton. Okay, so something to remember. And to remember also that the molecular weight of proteins usually range between 20 kilodalton and 100 well, 20 kilodalton, yes, so that means 20,000 daltons, and 100 kilodalton or 100,000 daltons. That's kind of where your most proteins are. You do have some smaller proteins, obviously, but that's kind of the range. And if they're larger than 100K, that means they are not really singular proteins. They are associated as a quaternary structure protein where you have several polypeptides associated together. Then they form a larger quaternary structure. For example, soy protein, legumin in soy protein, which is glycine, forms up to 300 kilodalton. It's a quaternary structure where it forms large molecular weight quaternary structure. So what do you think the linear sequence and length determines? So the linear sequence of the protein and the length of it determines what or affects what? We talked about this a little bit at the beginning. It's kind of like a refresher question.
The size of the protein.
Size of the protein, the length, basically size, but what else? The linear sequence.
What protein it is?
Yes, what proteins are, but what's specific about the protein? What specifics would it determine? So the amino acid composition and the linear sequence.
Nutritional value.
Very good, yes, nutritional value, but let's think a little bit outside of that.
Functional properties.
Functional properties, but before functional properties, it determines the physical chemical characteristics and the structure. So basically, the amino acid composition and sequence determines like the net charge, surface hydrophobicity, total hydrophobicity, how much reactive groups you have, what type of interactions can happen, and then the structure. Is it going to be a more alpha helix, more beta sheet? What kind of tertiary structure? A globular, an open structure? Is it going to form a quaternary structure? What kind of functionality? So the sequence is basically determining everything about the protein. So the sequence, the length, and then the actual composition of amino acid. Now there are certain things here I'm going to go into and you're going to go, why do I need to know this? It's important, trust me. It will all fill in the blanks later on. So we're going to talk about unique angles and the resistance to stretching and bending and flexibility. So we have a specific bond between the carboxyl group and amine group. And we call it the omega angle, and it has this 6 degrees in terms of the angle. So this is very inflexible. It's not flexible because it kind of it is a one bond, but acts kind of like a double bond. So you have electrons here on the O and electrons on the nitrogen that are not part of the bond, but they can be shared. When they are shared, so it becomes kind of like a partial double bond characteristics. When you have a partial double bond characteristics, you have minimal stretching and bending and minimal flexibility. So, so that is what explaining here that kind of the sharing of electrons between the oxygen and the nitrogen and that partial double bond characteristic. So it has minimal rotational flexibility, but we have two other angles of significance. So this is your chiral carbon, and then the bond here between the chiral carbon and the amine is your pi or phi, and this one here is psi. The one between chiral carbon and the carboxyl group. These, in theory, has maximum flexibility and rotation. So they can rotate, they can stretch, they can bend. However, that's in theory, okay? So in real life, they are really dependent on the R group. How big is the R group? And then the steric hindrance that occurs because of the R group. So they do have more flexibility than the omega in terms of turning, stretching, bending, but they are impacted by the size of the R group and the components of the R group that might cause steric hindrance. So this is a peptide backbone, and we have something we call peptide unit. So the peptide unit, it starts with a chiral carbon of one amino acid and ends with the chiral carbon of the next amino acid. That is one peptide unit, basically, what comes in between. This is what I just said, is that the phi and psi has theoretically 316 degrees rotation of freedom, but the rotation of freedom is determined by the R group. I already said that. And the rotational freedom, what does it affect, do you think? So if you have restricted rotational freedom versus very flexible, what does this, you think, impacts? Just putting things into perspective a little bit. Why do we care about this rotational freedom? What do we want to understand?
It affects what interactions they can have.
Interactions, yes, formation of secondary structure. So how does the peptide or the polypeptide bend and stretch to form certain interactions within the different residues of that particular polypeptide to form an alpha helix structure or a beta sheet or beta turn or random coil. So that rotation impacts, the freedom of rotation impacts what structure is going to take. Again, here is a reminder of the restriction of proline itself, because remember, then this bond here is restricted. It might be free in different amino acid, but the phi here is restricted because now you have the amine group is actually bonded to your R group. So you don't have that much freedom. That's why we call it, remember, we will be calling it a secondary structure breaker. So we have cis and trans formation, but in nature, the proteins, usually the amino acids in a peptide, form a trans configuration because this has the least steric hindrance because your R groups now are opposite to each other rather than next down in the same plane. So they are in opposite planes. So that allows for more flexibility and rotation. So, so it's more, we call it thermodynamically stable, is the trans versus the cis. When you have proline, because of its cyclic nature, you might see it more in a cis configuration than other amino acids. Okay, so peptide bond blockage, not blockage, sorry, cleavage. So like I said, when you have two amino acids and then they are forming a peptide, the equilibrium constant is really high. So you don't get to go back to amino acid unless you add some energy or make it happen. So the way to make it happen, to break the bond, so you can break the bond by acid or alkaline. So you can have hydrolysis at high acidity, like 6 normal HCl, or you can have hydrolysis breakdown of the bond at high alkalinity. So that's how you can break a peptide bond. When you want to determine amino acid composition, you often do acid hydrolysis. So you take the protein and you hydrolyze at high acid and heat over a long period of time. So you can break all of the peptide bonds into individual amino acids. So you can do amino acid composition analysis. However, often if you want to get exact quantification of all of different amino acids, you have to do hydrolysis using different means because acid hydrolysis, for example, destroys tryptophan and cysteine. So if you want to determine tryptophan, for example, you do alkaline hydrolysis. So you do acid hydrolysis, alkaline hydrolysis, and then another digestion with a unique added reagent so that you can measure cysteine and so on. So you usually do 3 different ways of hydrolysis to get all of the amino acids quantified. Of course, you can break peptides by enzymes. And usually this is what happens when you digest your protein. You have digestive enzymes and you just break the peptides by the enzyme. So enzyme reduces the energy needed for the chemical reaction to occur. So you would break these bonds. So you have enzymes that are specific, very specific enzymes like trypsin. They only cleave after lysine or arginine. So after the carboxyl group of a lysine or arginine, and that's the peptide bond that gets broken. So they are very, very specific. That's very specific enzyme. But some enzymes are non-specific. Pepsin is not very specific. It does like to cleave at I think this is phenylalanine and leucine, but many others as well. So enzymes differ in specificity. Some enzymes are endo enzymes, some are exo, some are metallic enzymes, requiring a metal group to perform the reaction. But we'll talk more about enzymes in the enzyme lecture. But again, peptide bonds are either broken by acid, alkaline, or enzymes. Okay, so now that's your primary structure. Now we're going to move on to secondary and tertiary structure. All right, so we need to talk a little bit about the concept of free energy and the steric strain. So basically, the proteins don't exist as a strand, and that is because of the free energy that needs to be contained. Okay, and then you have steric strain. So if we talk about steric strain, this again comes back to the the rotation of the angles or the bonds. So here, okay, so here what you have, it depends on the R group. Then the R group dictates the rotation and the restriction of the rotation. So the bending and stretching of the bond that happens causes free energy. Okay, so we have rotation, we have free energy going on, we have stretching, bending of the bond. So that's chaos, right? So we need to contain the chaos. So we need to contain the free energy by forming bonds. So then your strand of protein doesn't stay as a strand because there's a lot of chaos, bending, stretching, flexibility. So the energy needs to be contained. So gradually we start seeing intramolecular interaction containing the energy. So basically we have enthalpy and we have entropy, and that brings us to the delta G equal delta H minus temperature by delta S. So delta H, I call it enthalpy and order. So you can think of it as the order because all of the energy is contained by bonding. And the entropy is the disorder, the chaos. When you break bonds, you have chaos. So when you break a couple of hydrogen bonds or a couple of hydrophobic or ionic bonds are broken, your delta S, the change in entropy is going to be huge. You are going to create chaos. Then you have a negative delta G, and that's a spontaneous denaturation occurs when you have negative delta G. So when you have chaos, the protein opens up, and then to contain the chaos, it starts making other interactions to contain the energy. So you might see polymerization with other proteins, you might see reconfiguration within the protein, but then it's denatured. It's no longer the way it was before. So that's the concept you want to remember. You want to remember enthalpy is the containing of the energy by bonding different bonds. A hydrogen bond, we're going to talk about them, hydrogen bond, ionic bond, van der Waals, hydrophobic, and covalent. All of them contain the energy to reach to a stable form. So we go from complete chaos of a primary structure to secondary structure, which containing some of the energy, but we still have more energy to contain. We contain it, we form tertiary structure, and sometimes we need to also form a quaternary structure for the stabilization within the entire system. Okay. So now I'm going to talk a little bit about, we have 5 more minutes. I'm going to talk about the role of hydrophobicity and water in the folding of the protein. So that was one of the questions earlier. So the hydrophobicity is the driving, or the hydrophobic interaction is driving force for formation of secondary structure. But it's not the stabilizing force. It is the driving force. So try to remember that. Try to remember that hydrophobicity, it drives the formation of secondary structure. How? Again, we're going to talk about basic structure, okay? What happens, we said earlier, that you have that hydrophobic residues, they dislike water, they try, based on the composition and the sequence of the protein or the amino acid in a protein, they try to associate with each other. So they come closer to each other and expelling water out, okay? So water has tendency to form hydrogen bonds with the residues because of, hydrogen bonding is bonding between a hydrogen linked to an electronegative atom and a bond with a hydrogen and an electronegative atom. That's the hydrogen bond. Electronegative atom bonding to a hydrogen linked to an electronegative atom. Okay, so water tends to do a lot of that hydrogen bonding. So when it's expelled out, then we have hydrogen bonding forming between the residues or among the residues within that polypeptide. This is why hydrophobicity is the driving force of secondary structure formation. But the bond that stabilizes secondary structure is hydrogen bond. So you start getting hydrogen bonding formation because water is expelled to the outside. And then water forms hydrogen bonding with the outside residues. Anybody likes me to repeat? Good. So let's talk about the different interactions that can happen within the protein. So we have so many different interactions that can happen. So we have the dipole interaction, which can also be known as van der Waals interaction. So neutral atoms can interact, but it's a very weak interaction. And it happens when the distance is less than 6 angstroms. So at a distance that is less than 6 angstrom, you can have this type of weak interaction. It's weak, but it's additive. So a lot of van der Waals and or dipole-dipole interaction happens. So they add up in terms of containing energy. So they add up to the stabilization of the structure. Hydrogen bonding is very common. Like I said, an electronegative atom interacting with hydrogen bond to an electronegative atom. And a lot of amino acids get involved in hydrogen bonding, but the main ones are serine, threonine, aspartic acid, and glutamic acid. Most of the hydrogen bonding that happens stabilizes your secondary structure, mainly alpha helix and beta sheet. So you want to remember that. Another thing you want to remember is the 3-letter of the amino acid. So you want to know the 3-letter. There is also the 1-letter, but I don't know it. So if I don't know it, all of it, I will not ask you to know the 1-letter for amino acids. Okay, electrostatic interactions. So this can be repulsive or attractive. So if you have opposite charge, obviously you form an electrostatic attractive interaction. Or if you have same charges, then you have repulsive. And sometimes this becomes important at high pH and low pH. You start having more like charges, so you get repulsion and the protein structure opens up. So that's why we say high acidity or high alkalinity also denatures the protein because of like charges. So mainly you have your carboxyl groups and amine groups, but also you have the cysteine and tyrosine at alkaline pH. They become forming a negative charge, so they can take part in electrostatic, either attractive or repulsive forces. And then, of course, you have the basic and acidic amino acids here that are important. So presence of water also attracts interactions. So if you have charges, you have more interactions with water as well. So that's the question of effect of water. Hydrophobic interactions, obviously, with hydrophobic groups, phenolic groups, and then also groups of hydrocarbon groups. Disulfide linkages. These are your covalent linkages that can happen within the molecule and across, so inter or intramolecularly. This is an important table to remember because it helps us later on understand denaturation, impact of different reagents on breaking of bonds. So this is an important table. So here it lays out all of your different linkages. It starts with the covalent bond containing the most energy. So it's the most stabilizing form of linkages is the covalent linkage, and it stabilizes tertiary structure quite a bit. and it takes a lot of energy to break it, obviously. Then you have electrostatic interactions comes next in terms of containment of energy. So the energy that is contained in the bond is required to break it. So in order to break a bond, you need the same amount of energy that took to form that bond. So something to remember. And then you have hydrogen bonding, and you have hydrophobic interaction, and the weakest ones are van der Waals or dipole. So these are some of the functional groups that take part in the reaction. And then the disrupting solvents. So for example, covalent bond reducing agents, because here you have the disulfide linkages. So they are, when you have SS, this is the oxidized form, then you can reduce it into SHs by reducing agents. So beta-mercaptoethanol, you can actually use free cysteine as a reducing agent, DTT, and sulfides. If you want to break hydrogen bonding, heating, if you heat a protein, we're going to talk about collagen, and heating the collagen breaks down hydrogen bonding, you form gelatin, and then when you cool it, hydrogen bonding happens again, and then you form the gel, the gelatin gel. So hydrogen bonding gets weaker when you heat, and also in the presence of urea and detergents such as SDS. So those of you that run SDS gels in the lab, you know that we prepare the samples in SDS buffer. This breaks all non-covalent bonding. Hydrogen bonding is disrupted, hydrophobic interactions are disrupted with the SDS, which is a detergent. Hydrophobic interactions are also interrupted by organic solvents. So take the protein, put it in an organic solvent, then now the hydrophobic residues on the interior want to interact with what's outside. So depending on time of exposure, you can get denaturation of the protein and breaking of hydrophobic interactions. You can enhance hydrophobic interactions by heating. Electrostatic, changing the ionic strength, changing pH, you can impact the charge of the protein by changing the pH, and the salt can impact the load of charges, either shielding the charges or increasing the charge load on the protein. Okay, I'm going to stop here before going on to this concept here, which I talked about already, that when you break few bonds, such as few hydrogen bonds, you basically cause a lot of chaos. So delta S will increase, and then the delta G becomes negative, and that's where you have spontaneous denaturation. When it's positive, it's in the protein is in its native stage, and delta H is basically the summation of all the energy by the interaction. So we already talked about this, so we can just move on from here. Next time we can continue. All right, thank you guys. I will post the recording on the web, and please remember to come with some questions or discussion or anything next time. All right. Bye, everybody.